Hello everyone and welcome back. My name is Mr. Cobalt, and in this video I'm going to be going over how to find the pH of the following solutions. That is morphine hydrochloride and aluminum chloride in solution, which is going to form a complex ion. So let's get into this. Okay, so for the first one we have a 2.0 molar morphine hydrochloride, and they give you the formula C17H19NO3 with HCl, and they give you the pKb being 613. And so the first thing we want to recognize is that morphine is a weak base, and of course hydrochloric acid is a strong acid. So here we have morphine in a hydrochloric acid solution. And so what's going on here is, because you have the strong acid HCl mixed with the weak base morphine, that strong acid is going to react pretty much completely with the weak base morphine, forming what is the conjugate acid, right? So this nitrogen here with its lone pairs is going to pick up the hydrogen. And so we're going to have mostly in the conjugate acid form, and we can kind of write that generically. So what's going to happen is we have our base B is going to react with HCl, and it's going to completely form the BH plus ion plus, and then you got your Cl minus. So if B is your morphine, then the hydrochloric acid is going to donate, of course, H, and it's going to be picked up by the morphine, the weak base here, and it's going to form the conjugate acid plus this anion that is going to be neutral in solution. So we can imagine that the morphine is going to be in this form here, and so this ends up being a weak acid problem. And so because the strong acid that's in the solution with the weak base, it's going to push it all the way pretty much all to this form here as the conjugate acid. And so when we do this problem, we can do it as a weak acid problem. So then what we're going to have is basically we're going to have the morphine in the conjugate acid form, and that's going to react with water, and that's going to produce back the morphine in the weak base form, plus you'll have the hydronium ion. And so we can then do an ice table with this equation here. But the first thing we're going to have to do is we need the Ka value, right? But what they gave us was the pKb value. And so if you remember, Kw is equal to Ka, times the Kb. And so here we have the equilibrium constant with regard to the autoionization of water, and that's going to be equal to the Ka value of the acid multiplied by the Kb of its conjugate base. So these are conjugate acid-base pairs. And so here, if we take the negative log of each one, right? If we take the negative log of both sides, right, we get the negative log of Kw. So let's take the negative log of Kw is equal to the negative log of Ka times Kb. And if we use our law of logs here, this is going to separate into the negative log of Kw is equal to the negative log of Ka plus the negative log of Kb. Okay? And if you remember, if you take the negative log of something, that becomes p something, right? So the negative log of your H plus concentration ends up being equal to pH. So the P part of it means you're taking the log of that value, H plus concentration. Here, if you take the negative log of Kw, that's going to be pKw. And that's going to be equal to the negative log of Ka is going to be pKa. Plus the negative log of Kb, which is pKb. And so now we could use this equation to find the pKa, because the pKw is going to be 14, because the Kw of water, the equilibrium constant of water, is going to be 1 times 10 to the negative 14. So this is going to be 14, which is equal to the pKa plus the pKb, which they gave us, which is 6.13. So all we have to do is subtract 6.13 from both sides. And the pKa is then equal to 7.87. Okay, we've got our pKa, but what we need is the Ka value. And so as I said before, pKa is equal to the negative log of the Ka. So all we have to do is solve for the Ka value using our law of logs, right? So here, if we put in, this is the same as if I take the pKa, this is going to be the same as if I put the pKa as a power of something, okay? So if I could solve this, right, I could put the negative on this side, I could divide both sides by the -1, so that would make that negative, and then this would be positive. And then if I undo the log, that's like raising it to the power of a base 10, since that's log base 10. So then I'm going to have 10 to the negative pKa is going to be equal to 10 to the log of Ka. And so the log here and the 10 are going to cancel out, right? So that means that the Ka, 10 to the negative pKa is equal to Ka. And so all I have to do is find this value. So I have Ka is equal to the negative of the pKa, which is 6.13. Or no, I'm sorry, not that, that's the pKb. The Ka is right here, 7.87. So it's going to be negative 7.87. Oops, sorry. 10 to the negative 7.7. 10 to the negative 7.87. So now all I have to do is calculate that, and when I calculate that, I get 1.3489. So Ka is equal to 1.3489. Did I say 3489? 3489 times 10 to the negative 3, I believe. Negative 8. Negative 8. So there's our Ka value. So now that we have our Ka value, we can go ahead and do our ice table. So I'm going to write that down here. So the Ka is equal to 1.3489 times 10 to the negative 8. Okay, so we can now do our ice table. So we started with 2.0 molar. So we're going to have 2.0 molar here. We don't really care about the water. That's not going to be in our equilibrium expression. And then these are going to start off with 0 concentration to begin with. Since we have 0 product, it's going to make product, so it's going to shift towards the product. So we're going to lose an X amount here, and we're going to gain an X amount here, and we're going to gain an X amount there. Add these together, we get 2.0 minus X. This becomes X, and this becomes X. So now we can plug it into our equilibrium expression. So the Ka value, the Ka is equal to the concentration of our hydronium ion, so H3O plus, multiplied by the concentration of the base. In this case, it's morphine, right? Because we're starting with the conjugate acid form of morphine. So this is going to be morphine concentration, and then divided by the concentration of the conjugate acid form of morphine. So again, we're representing that as the generic formula BH plus. And so now we can plug in everything into our expression. So the equilibrium expressions here in terms of X, that's going to be X times X, which is going to be X squared, over 2.0 minus X. Now the question is, can we use the X is negligible or X is small approximation or assumption? And indeed we can, because if we look at the Ka value, that's very, very small, negative 8, 10 to the power of negative 8, compared to the initial concentration. So this is very, very small compared to this, and so we can bet that the X here is going to be so small as to be negligible, meaning that the concentration of the at equilibrium is going to be the same as the concentration that we started with. So we can get rid of X here, simplify it a little bit, and so then all we need to do is solve for X. So we have 1.3489 times 10 to the negative 8. That's going to be equal to X squared over 2.0. Multiply both sides by 2.0. And then take the square root, right? Take the square root of both sides, so that cancels out. Take the square root, and then we get X is equal to 1.642 times 10 to the negative 4. Okay. So as you can see, this is a very small number compared to 2. So this is definitely going to pass the 5% rule. But you can do the calculation by taking X, dividing it by 2, multiplied by 100, and you'll see that is definitely below 5%. So now we can use that to find the pH, because X is equal to this, which is the same as the morphine concentration, and the hydronium concentration, which is H+. That's what this is how we're going to find the pH, because remember, pH is equal to the negative log of the H+ concentration, or hydronium ion concentration, which is the same thing. So now all we have to do is take the negative log of that. So if we take the negative log, let me erase, give myself some room. So the pH is going to be equal to the negative log of the hydronium ion concentration, or H+ concentration. That's going to be equal to the negative log of 1.642 times 10 to the negative 4, and therefore we get a pH equal to 3.784, 3.784, and if we limit our answer to 2 decimal places, we can round that to 3.78. So the pH of the solution in part A is 3.78. Now what about B? Let's go ahead and do B. Okay, so for B, we have 0.50 molar solution of aluminum chloride, and then they give us the Ka value of this aluminum complex ion with water. Why are they giving us that? Well, the reason is because when you dissolve this in water, the chloride ion is just going to be a neutral ion. That's not going to do anything. However, because aluminum is a small, very highly charged ion, it is going to form a complex with water. So you get this aluminum water complex ion forming, and when that happens, because of the strong, relatively large charge on the aluminum and the small nature of this, you're going to get this these water molecules are then bonded to the aluminum metal here, forming ligands. The hydrogens on the water molecules become more acidic, so they can come off and form hydronium ions through the reaction with other water molecules. So so that's why they're giving us the Ka value of this complex when we're talking about aluminum chloride. So aluminum chloride, when you put it in water, is actually going to form the complex ion here, which is a weak acid. So this is a weak acid problem. So then we can set up our equation in a generic way, right? So instead of using this formula, we could just use HA to represent a weak acid generically, right? So here we have HA, right? That'll represent this. That's going to react with water to form the A minus, which is the leftover anion, and plus the hydronium ion. So then we can do our ice table for this. Let me get this out of the way. And so in this case, we have 0.50 molar to start with. So we're going to start with 0.50 here. We don't care about the water. And then we're going to start with 0 amount here and 0 amount there. So again, because we have 0 products, it's going to shift to make product. And so we're going to lose an X amount here. We're going to gain an X amount there. We're going to gain an X amount here. And then add those together. We're going to have 0.50 minus X. And this is going to be X. And then this is going to be X. Now we can set up our equilibrium expression, our equilibrium constant expression. So we know that Ka is equal to the concentration of our A minus, that anion that's left over, multiplied by the concentration of the hydronium ion, divided by the concentration of the acid. Again, we don't put water in. Water liquids and solids do not end up in the expression, the equilibrium constant expression. So now we can substitute and plug in these expressions for the equilibrium concentrations. And so x times x from here is going to be x squared, because we have x for both of these, and we plug in this for the HA concentration. So that's going to be 0.50 minus x. And that's going to be equal to the Ka value, 1.4 times 10 to the negative 5. And again, you can see here that we have a 0.5 versus 10 to the negative 5. And so again, this is going to be very small compared to the initial concentration. So that indicates that x is going to be negligible in this case. So we can go ahead and ignore x. So this change here is so small that the equilibrium concentration here will be the same as the initial concentration here, because subtracting x is really not going to affect that value there. So then we can rewrite this as 1.4 times 10 to the negative 5 is equal to x squared over 0.50, because we got rid of the x there. And so now all we have to do is multiply by 0.50 on both sides, 0.50. That's going to cancel out, and then we just take the square root of both sides, and we get x is equal to 2.645 times 10 to the negative 3. And since that's x, and x is equal to the concentration of the hydronium ion, right, H plus, then we could find the pH by taking the negative log of the H plus concentration. So the pH is equal to the negative log of 2.645. 645 times 10 to the negative 3, and then that's going to be equal to, so the pH is then equal to, if I take the negative log of that, I get 2.577, and if I round the 2 decimal places, that will be 2.58. So that is the pH of this 0.50 molar solution of aluminum chloride. That's it for this video. I hope you enjoyed the video. I hope this helped you in any way to help you understand how to solve these type of problems. And if it did, then by all means, like the video, share the video, hit that like button. Also, make sure you subscribe to my channel. Help me out. Hit that notification bell up there. When you do, click all so you can be notified by all the videos I put out. And finally, put a comment down below in the comment section. Let me know what you think. Ask me questions. I would love to hear from you. Thanks for joining me, and have a great day.